And here we go. Good evening, folks. This is David here again, and I'm here live for another attempt at finishing some of these projects. Last week we spent a lot of time talking about the new TinyVU board that's in development from Expat Audio, and I want to take a little bit of time this week to talk about some of the software that's been developed, show the board working live now that I have another webcam, and maybe take you through some of the steps that we go through at Expat Audio. I'd like to say best practices, but just our practices really, and solicit feedback from you as you guys see fit. And so what I thought we would talk about today is, here we go, the release and naming process. So when you do see a board from Expat Audio, when you're reading the manual, you have some idea of what we're doing. I'm going to go through a quick recap of the TinyVU hardware, that's HW hardware. We're going to go step by step through some of the revisions, so see some of the errors that I made in the original layout, and some really stupid things which I'm still nuts about, but you've got to expect them. We'll have a look at some of the software flow, some of the issues with the original software, and then we'll also talk about an add-on board that's already been requested based on some of the discussion from last week. And so yeah, we'll cover that. I don't expect today's show to be anything more than sort of half an hour or so. So if you just want to switch us on, leave us on in the background and so on, go ahead and do so. All right, so let's get started. So for the release process at Expat Audio is really based on something I do day to day, which is in the semiconductor industry, and we name all our releases at PG X.Y. So X would be like a major schematic change, and then Y would be like a minor change, like a layout change, or maybe a change of form factor in one way or another. And so if you're getting a PG 1.0 board from Expat Audio, and you actually see it on the board, it says PG 1.0, you know that was our first release of the board, and we're happy with it. And if you actually look in the user's guide, then it'll actually tell you what the latest PG we're actually running at as well, so you know very quickly. This is a, this board here is a 1.0, the latest one in the manual is 1.2. What differences do I need to know about? Okay, so for instance, the TinyVU board, so the one that you can see hammering away down here, actually is 3.0, and I'll explain how we got to there. The other thing we do as well in each project, we now share them on Dropbox internally between Keith and I, Expat Audio. But previously we had what we called an SVN, a subversion server. Subversion is a version control system, and so what we had was a trunk folder. So day-to-day development happens in the trunk folder, and then when we do finally sort of sign off on a PG, or we send the PCBs to the fab, we'll actually make a copy of that entire folder and put it in the tag folder, so we can then see what they are. And so let's see if I can find one of those. Dropbox, Expat Audio, projects, and then let's have a look at level meter. Okay, so we actually use the main folder as the trunk here. So that's a slap on the back of the hand right there. And then in the tag folder here, we'll keep, for instance, PG1, PG2, 3, and 3.1. All right, so that's what we go through. And when you read users guides from Expat Audio, it'll make a little bit more sense, I hope. So if you go step by step through some of the revisions, the original version of the TinyVU board had a onboard 5V 3.3 volt regulator for the MSP430 that's used to do the conversion. It also had an LM324 op amp, so it's a cheap and cheerful op amp because this is more of a visual aid rather than something I'm going to be listening to at some point. So it uses the LM324. The problem with that was it actually required then an additional power supply to do a positive and negative rail, because the op amp typically requires a ground center, so you have positive and negative. And so what that meant for us was we had the added cost of the regulator, and then you had to have a bipolar power supply in your system. So if you're building a 19-inch rack, with maybe, I think we calculated 35 or 36 of these all in a row, then it would mean that you had to still have a big transformer with a linear power supply just to do a front end op amp. So very quickly we moved on to the PG 2.0, which had a single 3.3 volt input. And so you had to have an external 3.3 volt source, but you were looking after a lot of op amps with it. So you were looking after the op amp, and you were looking after the MSP430 and all the LEDs. So it all lined up on one power supply, which you can buy as a brick from Alibaba, or even roll your own if you need to. Single supply power rails are always much easier to generate and make than dual rail power supplies. So we got the hardware for PG 2.0 more or less working. And then we had then I panelized them, which means to take the design and actually make four versions of it on one PCB, and that one PCB is probably about sort of 4" by 4", and that allows me then to put it into the pick and place machine that we have, and the pick and place machine is used in assembly, and so it picks up parts, pops them down. So the more I can do on one board at one time reliably, the faster the whole process. So panelization, we added a couple of GPIO pins and added a new potentiometer, which sets the trim for the input. And so there's lessons learned there, which I'll talk about a little later on. Okay. So you can see here we went PG 1.0, PG 2, and then PG 3, and then PG 3.1 fixed an error, which I think is on my next slide. But we'll come back to that in just a moment. So just to bring you guys back up to speed, based on if you didn't catch us for last week's show, we had a single. The hardware overview for this product is that we have a single-ended input into an input buffer with a plus or minus 10 dB trim. So that means if you have a cell phone input, it's not the end of the world, right? A cell phone input will you just add more gain, but if you're bringing in something really hot, then you can attenuate the signal as well. We run that into an external precision rectifier, and the precision rectifier essentially turns the negative signals from the wave upside down, and so what you end up with is a single-sided wave, and that means you can run that then into the ADC of the microcontroller very easily. We did that internally to the part because the ADC and the microcontroller, there's two ways you can do it. You can either do it externally, and then you get all 10 bits of accuracy from the ADC. It's only a visual tool, so 10 bits is enough. Or you can actually do it. You can do that rectification in software, but then you lose 1 dB you lose 1 bit of dynamic range. You lose 6 dB off it. To put it into perspective, roughly every dB, every bit in your converter is worth about 6 dB of dynamic range. So if we had sacrificed one of the bits, then we would have gone from 10 bits, 60 dB dynamic range, down to 9 bits, which would mean 54 dB dynamic range, give or take. So I wasn't quite ready to do that because I wanted the entire dynamic range as much as we could. So that happens in the ADC, in the software, SW, you can see it here. We do a low pass filter in the comparison and so on. And you can see the board, you can see it working. Let me jump to here. So I've actually got a little drum loop running into this. You can't hear it right now because we probably have some kind of feedback, but you can see that it's a drum hit, and then there's a peak hold going on there, and some filtering to create to be accurate to the VU standard, which is the integration time, how long it takes for a lot of power to increase the level. All right, let's move on. So back to there. All right, so some of the errors we made in PG3, and this was just really irked me. So in Eagle, in CADSoft Eagle, which is the tool we use, you can basically tell the software anywhere where I haven't drawn another trace, then you need to. So one of the issues we did here, one of the issues with Eagle here, you tell Eagle, okay, anywhere I haven't put traces down, you may fill with ground. But there are specific rules so that you can only fill ground in through a specific gap, and I wasn't paying attention to that. And so what you can see here, right here, is that ground didn't flow out from under the MSP430 to the rest of the product. And so the MSP430 was getting a 3.3 volt rail, but it wasn't getting ground, and so it wasn't even powering up. And so for some of the dev boards, which include the ones I have here, I had to drill a hole over here, tie top and ground tie top and bottom ground together to get it to conduct and so on. Alright, so let's move on a little more here. So from a software flow, and I'll show you some of the development tools as well, I am the world's worst software developer. Really bad. I kind of hack it together and see if I can just get it to work. But essentially what we do is we set up the device, so set up which pins are going to be LED outputs, set up the clocks, and so on. And I think I can show that here real quick. This is Code Composer Studio. This is TI's software tools for developing with MSP430. So we define a couple of the bits here. So we define, for instance, the UART transmit and the UART receive. We send some bits which are actually connected with a software UART to handle that, a software serial port, so that you can hook it into one of those USB serial port devices, and off you go. And then we set up the coefficients. So these are setting up the thresholds for the comparison in the device. And then on top of that, then we add a whole bunch of other variables and so on. And then we start the program where we set up the device to run as fast as possible at 16 megahertz, which is pretty mind-blowing. I think back to, you know, the days when I had like a Commodore Amiga, and that was running at 7 or 8 megahertz, and yet this one is running up at 16 megahertz. It's incredibly fast in comparison. And so, you know, it's. I still wonder if we could have even done this on an Amiga in that case. But anyway, so from there we set up the actual ADC to start the various conversions, and then we set up the LED output pins. All right, sorry about that, folks. So we do, for instance, a quick startup. We test to flash all the LEDs if one of the jumpers is put in, and then from there we start this infinite for loop, okay? And that's represented by this for loop that starts here and comes back around again. So the first thing we check is if any data came in from a serial program. And to give you an example of what we have in the serial program, this is the GUI, if you will. So this what you see here is a serial window that's running. It comes from everything you see on the screen here is actually being served up from the board. Okay, so for instance, if I want to see what the thresholds are, then I can tap into the device, and what it's actually doing, it's actually telling me that you know, for instance, the ADC values are all the way down to 10, all the way up to 1024. So what comes in from the ADC is a value between 0 and 1024. And for each of these thresholds, then the appropriate LED lights up. So, you know, when I press enter, for instance, here, what's actually happening in our software is the software itself is saying, oh, something happened, he pressed enter. Okay, well, I'll slow down to 1 megahertz, transmit the data, and you know, echo the data back, or if the buffer is full, pass the entire thing. So for instance, if I want to set a threshold, change a threshold, I can go back to my here, and I can say, okay, if I read first, and let's say I want to set this LED coefficient to be a little bit lower so I can catch peaks, I would say write LED number 9, 10, 20, and you'll see here it hasn't done anything yet until I press enter, and at which point if I press enter, there we go, now it's catching all the LEDs that are working, and you can see that if I go full screen here, oh, there's wires in the way, hold on, let's see if you can move these back. So I'm getting all the LEDs now catching the peak all the way up, see? Okay, so that's processed. We start the ADC for one sample, so it's just doing a quick sample. The device goes to sleep, and then when the ADC is ready, which is about 13 samples later, 13 clocks later, it wakes up, it reads the raw data coming in and uses that as a peak hold, and then it does a little bit of filtering, and it sums both the data. So what you're seeing here, you see the peak and then the average data are both output at the same time. All right, so let's go back here. All right, so that covers where we are, and you know, there's one or two other things I wanted to show here while we're at it. So in fact, that'll do there. I have some secret modes in here as well I can respond. So for instance, I have a test mode for all the LEDs, so that when they come off the manufacturing bench and we plug them in, all LEDs on, it just ignores the audio is coming in and switches on all the LEDs on the board, which is wonderful, right? Because you know very quickly if you have a soldering issue or not. This is a mode where I'm not doing any filtering whatsoever, so the response is very, very, very quick. I'm not sure. Let me jump to the full screen so you can see that. Yeah, so you can see, you know, it's catching peaks. You know, there's no kind of integration time to give you an idea of like the average level or anything. It's just absolute. And then finally, let's jump presentation. There we go. And then the final mode then is the one with some VU filtering going on. And you know, you can see that if I jump to full screen again, you can see, you know, the average is actually lower because it's taking longer to integrate. That's actually the real behavior of or an emulation of the real behavior of a meter. Cheers, by the way. All right, so following last week's broadcast, I was talking to one of my previous customers, and I was saying, hey, what do you think of this board? And you know, the feedback was, well, you know, cool stuff, but you know, 10 LEDs really isn't enough. You know, he was looking for something that could actually emulate a plasma VU meter. And for those of you that aren't familiar with plasma VU meters, let's have a look here. I did a Google image search for you in advance. Isn't that great? So the plasma VUs use a different technology than LED. They use plasma, and they actually have a very, very, very detailed or very granular separation. So this is actually one that was done by Igor at IJ Research. But you know, the actual plasmas themselves are difficult to get hold of these days, and you know, they're very expensive and very complex to drive. Whereas, you know, what I was considering doing, or what I was asked to do, is actually do one with LEDs instead. And with surface mount LEDs, we can actually pack them in really, really densely. And to give you an idea of, you know, surface mount LED, let's have a look here. Surface mount LED. Alright, so you can see here. So the ones I would probably use are 0603s. You can see here they're like less than 1/5 of an inch. So I believe that's inches, right? Oh, am I going nuts here? Yeah. Okay. So we can do really, really dense stuff with that. And so okay. So sorry, I got distracted. I was looking at the chat for a moment there. It's hard doing all this solo. You know, at least Lady Ada over at Adafruit has that guy helping her out as well, Philip. So all right. So let's go back to the spec. So the spec, we needed a minimum of 56 LEDs, a constant intensity per LED. So, you know, for instance, if you have a yellow one or a green one or a red LED, you want them to be more or less even in how much light and how intense they are. Ideally controllable from the existing board, so I don't have to redesign another board again to you know, do this. And then 1 dB per LED ranges from 18 dBu, so you know, way beyond clipping, down as low as possible at the other end. And so, you know, I'm sharing with you here some of my initial thoughts, and then I might step into doing some of the design for about 15 minutes and so on. But I really wanted to use simple shift registers to do this. Shift register is a product where you, with a clock and a latch, you clock in some data. So let's say you want 4 LEDs to light up, but the other 4 not to. If you have 8 in total, you want the first 4 to switch on, the first 4 off. You would send 4 ones, 1 1 1 1 1. That's 5%, 1 1 1 1, and then 4 zeros. Basically, you clock in 4 zeros after it, and then you latch, and at which point 4 of them the LEDs will switch on, 4 of them won't. If you do it fast enough, then you don't see it happening in real time. So the other thing I was going to do was to use constant current sources and current mirrors to match the intensity as well. And so one of the tricks we can do here, normally with a I need to get a whiteboard for this, don't I? You know, what do they call it? DaveCAD. But typically you'll have you know, the voltage, the diode, and then you'd have a resistor underneath that sets the current, and with that sets the intensity. Well, there's a few limitations in doing that. One of them is that you truly want a good matching between all the resistors, but also LEDs don't drop, depending on the color, they don't drop the same voltage. So let's say I use a 100 ohm resistor in line with my diode. The red LED could drop less voltage and therefore drive more current through it with a simple resistor. And I'll come back to that next week, I think. The whole concept of using current sources and mirrors for LEDs is pretty cool. But the other thing I was thinking about is, what if I want to be able to, on the front of my product, have a knob where I can dial in, how bright I want the VU to move at. And so if I have constant current sources looking after my red, my orange, and my green LEDs, then I should be able to control those with PWM, pulse width modulation, which means, if you only want it 60% of the brightness, you only switch it on 60% of the time. So you switch it on and off really quickly, and that on and off ratio then is the PWM. Now on the software side of the house, I was really very, very concerned about adding more processing time to this. So for instance, if I go back to the software flow, you can see that the ADC is manually kicked, manually prodded to start converting. And so the faster I can go in this loop, the faster my ADC runs. And so if I run too slowly, my ADC may run so slow that I don't catch high frequency content, and that's something I worry about. So the key here is get through that process as quickly as possible. So the challenges there are to minimize the additional processing, and the other thing is when you have 10 LEDs, I have to do 10 comparisons to see, should I switch LED number 2 on? Well, LED number 2 is, if the level from the ADC is higher than this or lower than that. In fact, I can show you this logic running. Let's go to the next one. Here we go. So I have a bunch of if statements that run after the other, and so I say, if the VU value is bigger than coefficient number 2, then switch those two LEDs on. And it works pretty well. But the problem is, that's fine for 10, but if I actually have 40 or 56 LEDs, then that adds many, many, many more instructions. So I really want to find a smarter way, a faster way of doing it. And so that's something I've got to kind of wrestle and get my head around. Any advice on this, please put it in the comments. I'm a terrible software writer. There are people that are much, much, much better. And then the other thing is, how do I convert the levels to light up in 1 dB steps? So for instance, my value coming from my ADC is, my maximum value is 1024 or 3FF. But that's, in 16 bits, that's 6 zeros and 10 ones, right? Well, actually, my string is 56 LEDs long. So somehow I've got to take, this tightly packed number and expand it out. And the equivalent in decimal terms, let's say I have 50, pick a number, 28, okay? Well, in true numbers, that's only a 2 underneath. That's only 2 items. I actually need to expand that out to a true 28 quantity. So I've got some ideas on how I can do that. Again, that's a software issue, so I'll probably address that a little bit more next week. And in the meantime, by next week, we'll also begin the process of releasing the TinyVU board, the original one itself as well, and start doing the initial build. Okay, so let's. So the process from here to do this other board is first to build a block diagram, begin pre-selecting the devices, and then qualify as many jelly bean devices as possible. And this is something that a lot of folks doing Kickstarters and stuff forget or fail to do. They find the most awesome part for the job, and then they realize that they can't source it cheaply. It's hard to get from Mauser or DigiKey. Forget sourcing it in China. If you try and source it in China, it ends up being more expensive than just buying it from Mauser or DigiKey. So really, some of the work that folks at Dangerous Prototypes do, and Adafruit and SparkFun, these guys, they all keep a list on their website of jelly bean parts. Really try to have a look through there to see if you can find a solution. In my opinion, it's sometimes cheaper to buy 2 jelly bean parts than it is to actually buy the high-end part that's all integrated as well. It's really worth checking in. Unless you're space constrained or power constrained or some other constraint, it's really worth looking at them. All right, so here's one we made earlier. So this is Microsoft Visio. I just use this just to capture ideas, and this is how I plan on building the 60. This just shows 16 LEDs, right? We have to build enough to go out to 56, but it all scales. So a shift register, which we'll look at in a moment on a data sheet, and then a current mirror, which a constant current source. We'll show those in just a moment, and then what you see here, and I actually need to label these, is a latch. Pop that there. A serial clock. Now, the serial clock is pretty important. The serial clock actually helps the device know when you're ready to clock in true data over here. So imagine you have 5 ones next to each other, right? So you go 11111 Well, it requires a serial clock to tell the shift register, hey, this is a 1, and this is another 1, and this is another 1. Otherwise, it just sees one big block and it doesn't know what to do. And so the data is actually daisy chained through the devices, while the serial clock is equal to all and the latch is equal to all. And what the latch does, it basically says, okay, you now have these 8 bits in your memory. Latch those onto the LEDs so that we can start tickling things through the shift registers again. And so let's have a quick look at the shift register, and then we'll also look at the current mirror and the constant current supply. All right, so this is a TI part. It's an SN74HC595, and with many of these 7.4 series logic devices, typically people just remember the last 3 digits every time. And so the 595 here, so from a microcontroller you have 5 lines coming into it. You got a serial clock, you should have serial data, you should have a latch clock, and then methods to clear the devices or enable it as well. And then what the example schematic here is, a bunch of LEDs and the appropriate current limiting resistor, and that's pretty easy to use. The challenge there is that red is going to require one value of resistor, orange is going to require another, and green is going to require a different one again. That becomes a bit of a pain to manage, and so we can use things like current mirrors and so on to manage that a little easier. And given the price of some of these transistors and so on, it's not something that adds a significant amount of cost. So if you look at the, let's have a look at the timing diagram, and this helps me understand how this part works. And so let's see. So here's your serial clock coming into the device. Here's your serial data coming into the device, and another clock source. And essentially, you can clock the data into the device. So you send a whole bunch of pulses to the device, send a serial data that much, and it tongue through each of the outputs. So it's very, very easy to use. There's some great tutorials on some of the Arduino type of websites as well on how to use these. And the nice thing is you can daisy chain this for as long as you like. So if we have a customer come in saying, hey, I want a 112 LED version, that becomes possible as well, you know, if required. All right, so let's see. Let's borrow this. Current mirror. There's a wonderful article, even on things like Wikipedia, on current mirrors. I'll borrow this image for now, though, to explain the current mirror. So the current mirror here, this is using you know, very low cost NPN transistors, but essentially you create one circuit at the beginning, it gives you a reference current, and then you connect that through multiple. So each of these could be like one LED, and you have one transistor per LED that sets the current through the device. So very, very, very easy to use. And then, you know, my transistor of choice for this kind of effort is the old 2222. So they used to be called PN2222s. In fact, I could probably, here we go. PN2222s. These things are as cheap as chips. And essentially, because I'm just using one per LED, they're almost cheaper than the LED. And to give you an example, let me just put the datasheet real quick, and then we'll have a quick look on eBay to give you an example of how cheap it can be. So these devices, you know, they'll handle up to 500 milliamps. They'll take ridiculous voltages, 40 and 75 volts, up at their absolute maximum. Let's see. The only thing I am slightly concerned about is the capacitance on them. So, you know, what tends to happen is if you switch into them too quickly, then they can that switching doesn't become complete, and you could actually lose some signal there. So that will need to be evaluated a little bit more. But probably by next week, I actually have a little proto board. You know, we will, you know, drop these pins in, wire them up by hand, and so on. But just to hopefully my history doesn't show up here, but here we go. PN2222A, and you can see here a PN222A, 4,000 of them is $22. I mean, it's ridiculous. So you know, they at that point they're virtually as cheap as the LEDs themselves. Not as cheap as surface mount resistors, but still, you know, if they can give me good matching across everything, then it's a very cheap way of getting to market. So it's been pretty quiet on the chat tonight. I don't see much going on this, so I'm probably going to call it to an end at this point. We'll start next week with the Eagle design, and we'll talk a little bit more about what it's like to actually release these products. One other thing I wanted to do real quick was to show you guys the response of the VU meter. I actually have. So right now there's two different media players driving the VU meter that you see here. So I can play some of the speakers, but I don't have a Y cable to put exactly the same signal, but I can put the same song into both. So bear with me while I try and show you guys how we do this. So you can see that it's a very basic loop, and yeah, you can see there's a transient response, and the average level is much lower, which is why there's so much disparity between the top and bottom there. So these boards will be available soon. The planned pricing for them, you'll get 4 of them in one batch, and it'll be I'm expecting about $99, but it'll be, you know, all in, very easy to use, yeah, you'll be able to snap off the board if you need to make, you know, you can snap off the board at this point here. So you can see there's a little V groove here. So if you want to use the LEDs that are here, you can just use little wires and solder them over. Or, let me turn this down now. You know, you can make your own LED array in your front panel with regular 5mm LEDs or 3mm LEDs, and wire them directly. So very easy to use. Yeah, if you have any questions, you're welcome to come to the Expat Audio group on Facebook. So that's www.expat.com. facebook.com/expataudio, or add comments here to the video once it uploads. And until then, folks, thank you very, very much for your time. And yeah, signing off. Thank you.